Sir, I don't understand what you mean when you say boosts.
Oh, yeah, I think I explained in the last lecture, but so the boost, yeah, that's a very good question. So in special relativity, you have some reference frame, say. Okay, so let's this be a reference frame. Let's call this S. This is x-axis, this is y-axis, this is z-axis, okay? Now, what special relativity tells us is that the physics is unchanged in all inertial reference frames. What is so if S is an inertial reference frame, then what would be another inertial reference frame? Another inertial reference frame would be, say, a frame where, you know, S, we have another reference frame, let's call it S prime. So this is S prime, and this is this is X prime, this is Y prime, and this is Z prime. But this new reference frame is traveling with respect to the last reference frame, say by some velocity. It could be in any direction, but let's take it in the X direction, V. Okay, so if you are an observer in S, you will see S prime is moving with a constant velocity, V. So both S and S prime are valid reference frames, right? But S prime is known to be called boosted with respect to S with the velocity V. Now, if you are an observer in S prime, what will you see? You will see the reference frame S traveling in the opposite direction with the opposite velocity, right? So in that case, you will see that the reference frame S is boosted with respect to S with the velocity minus S. So do you now understand what boost means?
Oh, yes, I guess. Do they ever cross each other?
Yeah, of course they can cross each other. They're just reference
Okay.
frames. They're abstract objects. But you know, you can have a passive sense of boost. You can have a like an active sense of boosts. So, for example, if I'm like kind of, you know, standing here, and there is a rocket, and there's a payload on the rocket, and the rocket is moving with some constant velocity v, then I say that the rocket has been boosted. Okay, so boost just means that something, a Lorentz boost means that it's the motion of another inertial reference frame with some constant velocity. Okay, as you can see, there are 3 parameters for a boost, right? You can boost something in X direction, Y direction, and Z direction. And these are the, so for example, you know, remember that we talked about the, in one plus one dimension, we talked about the Lorentz transformation. It was cosh of zeta, sinh of zeta, sinh of zeta, and cosh of zeta, right? And we can think of it as part of a 4-dimensional Lorentz transformation. So this is a boost in the X direction, right? So this matrix, this whole matrix, is a boost in the X direction. Okay, it's not a rotation. And we can show that by going to V, which is tan hyperbolic of zeta. Okay, so we can convert these to, say, gammas and betas, right? Okay, Fiza, have you ever done any special relativity before?
None at all.
Yeah, it's probably that's why. We should probably have like maybe a tutorial on special relativity. What do you think?
Sure, sir.
I think that would be helpful. Okay.
Okay, sir.
Okay. So any other questions? Okay, so let's make another comment, the next comment. So the group SO2, N is actually physically relevant. And it's called the conformal group. In n+1 dimensional Minkowski spacetime. And what it does is that, rotations preserve the length of vectors. The conformal group doesn't preserve length, but it preserves angles.
Is this related to the conformal field theory?
Yeah. Angles between vectors and curves. Okay. And this is very important in physics. As Farhan was saying, it is related to something called a conformal field theory, or CFT. CFTs describe, for example, amongst other things, describe the field theory of condensed matter systems at second order phase transitions. Okay. If you take a statistical mechanical system and you see that it has a second order phase transition, then that particular phase transition, some of the important physical parameters at that phase transition will be captured by some CFT. So this is something that has some application in physics. Not only that, string theory is actually a form of CFT. So there's a huge application of CFT in string theory. And also there is a emerging field called holography, which is a new way of understanding quantum gravity in terms of a dual quantum field theory. That is also a conformal field theory.